So the company name is KP Labs, and today, along with Michał Gumiela, who is our system engineer, we'll show you some examples how the onboard data processing and AI could be used in space. So just to give you a short introduction about us, why we are here, why we have some expertise in this area. So we are from Poland. The company was established in 2016, and right now we are almost 60 people. And if you look at our competences, our products and projects, we could split them into 4 areas of interest, which is imagery, software, computing, and AI. And AI here is the most crucial, most important part. So if it goes to the project summary, just to give you all some understanding of what we are doing, within these 5 years, we've completed 8 projects. Right now, ongoing, we have 12 more projects. We are about to start 4 big projects within the next 1 to 2 months. And the overall budget for these projects were over 10 million euros. So why we are speaking about onboard data processing and AI in general, why it is so important for space. So first of all, if you look at different predictions and different researches, one of the example that I found is created by Euroconsult that within 2020 and 2029, almost 12,000 satellites will be launched, where over 1,000 satellites will use onboard data processing, which is over 100 satellites a year, which is a huge difference comparing to what we have right now. And according to different research predictions for 2030, we will successfully mine the moon for water by 2030, or we will operate assets remotely on the moon. We will manufacture in the space directly, or AI will be commonplace in space. So if you think about areas of interest, area of space where it could be used, so it could be Earth observation with increasing the efficiency of satellite images that we use today. According to different numbers, we are using around 15% of all satellite imagery data, which means that thanks to the cloud detection or to some bit pixels mitigation or some other techniques, we can increase this number. Another area, it could be risk management that will be beneficial for us as people on the Earth. There's also deep space with some delay in the communication, and we have to have autonomy and semi-autonomy in this area, and this is must. There is also space debris emissions, and there are more and more companies, more and more agencies that are interested in space debris. And SSA, SST, this is something where we could also use onboard data processing and AI. And last but not least is human flights. Not only flights, but also human inhabitants that are about to happen on Mars or any other planet. So this is the areas that are quite important for us. And about our products as a company, what we are doing, we have smart mission ecosystem, which is hardware, software, and algorithms combined together, where everything works with everything. So we have like Oryx, which is modular onboard software. We have Antelope onboard computer. We have Leopard, which is data processing unit to process and pre-process data on board a satellite. There is also Lion, which is bigger brother of Leopard, dedicated to bigger satellites. And of course, there is the Herd, which are a bunch of different algorithms for Earth observation, but also for telemetry data analysis to check whether everything is working correctly with the satellite. And of course, there is Oasis, which is UGC, and the idea that we want to check beforehand if everything works correctly with the satellite. So the idea of this product and our projects in general is that on one hand, we want to increase mission processing capabilities and mission safety and control on one hand, but on the other hand, we also want to reduce mission development time and mission costs, because it is super important in case we're speaking about constellations or mega constellations. So this is where we see a huge potential for onboard data processing and AI. And here where I pass the word to Michał Gumiela, who will speak about more technical issues.
Yeah, thank you, Helena. Thank you all for joining us. So my part of the presentation will be a little bit different. I think that you're already convinced about values behind in-orbit processing. So I would like to touch the challenges and discuss with you how to tackle them. So apart from growing interest and clear benefits coming from the edge data processing, when you think about on-orbit processing, you would probably end up with a problem of constrained resources in multiple areas. Just to name a few of them, so you can think about computational resources, especially for AI, that could be limited for many space-grade platforms. Available power and heat rejection capabilities for your satellite platform might be another constraint. Of course, additional mass and volume for additional data processors might be not available in your mission, in your budgets. So at KP Labs, we designed integrated solution to cover most of the payload needs by a single device. So you can perform data acquisition from your instrument. You can have large volume storage, data pre-processing capabilities. What is especially important to us, AI processing acceleration, just in a single device. That would normally be essential part of the satellite, essential payload computer. So we propose adding such value to your normal payload computer. And we propose here a very flexible architecture consisting of radiation hardness supervisor to increase robustness of the mission, up to 2 Zinc ultra-scaled MPSoC consisting of ARM CPU and FPGA to cover multiple applications and multiple algorithms and use cases, up to 1 terabyte of PSLC flash memory, reliable non-flash memory, and plenty of RAM with error correcting codes. And of course, a bunch of external interfaces to keep the solution compatible with different instruments, radio, OBCs, so that Leopard, the processing unit I'm talking about, can be all you need for payload management with data processing capabilities. And this is exactly what I would like to present you, taking a hyperspectral satellite mission, Intuition 1, as the exemplary use case, that apart from the platform satellite bus, consists mainly of just 3 components. So we've got hyperspectral instruments. In terms of the electronics, this is just an image sensor. And the central part is Leopard DPU. And the third component, very important in the onboard data processing, the processing algorithms, both classical and deep learning based. So all of those 3 components cooperate with one another, allowing us to create an onboard data processing pipeline. So we start with raw frames from the sensor that are transferred to the Leopard DPU as an enormous stream of data, like 6 gigabits per second. IP core in the FPGA part of the Leopard is used to receive and store the data. Then we may use various pre-processing algorithms, perform co-registration of the data, radiometric processing, and so on, to obtain hyperspectral cube. After that, a cloud mask is created to filter out useless data to avoid further processing. Also at this step, we can store the data for further downlink or compress it or so on. And then clear parts of the imagery of the data are processed in the most important step, the value extraction. So of course, we don't want to downlink the whole hyperspectral picture. It's really essential when we are talking about hyperspectral pictures. It may be also very essential for synthetic aperture radar data and other multi-dimensional or quite big data. So we want to make use of our segmentation and classification algorithms to select only the data that is really interesting for us. So basically, we can transform hyperspectral scene with multiple bands just to one 2D image, consisting, for instance, of pixels classified to the classes that we want to find on the picture. So taking this in numbers, that means that we can squeeze our typical 50 by 50 kilometer scene from 1,500 megabytes to just 4 megabytes of data. Of course, we need to first train the algorithm. So this is quite important and quite big challenge for in-orbit data processing. We need to train the data for a particular use case. Of course, we can use the neural network architecture multiple times, and the architectures can be reused for multiple problems. Of course, the typical use cases cover agriculture, including disease detection, surface type classification, and even soil parameters mapping that we are working currently on and fine-tuning our algorithms to demonstrate it in the practice. But as I said before, when we are thinking about on-orbit data processing, we always keep in mind the resources. So the questions may arise, is efficient AI inference on embedded systems suitable for space application? Is that possible? So we prove in our research, recent research paper that's true. So benchmarking deep learning for onboard space applications tackles various image processing problems to cover multiple use cases. Free state-of-the-art deep learning models for Earth surface segmentation, for object detections, namely in that case, crater detections on moon surface, and the last one for Mars surface classification. We've proven that performance of over 2 tera operations per second is achievable just on the single processing node of the Leopard, and you can have two. For our most computing intensive model, we got 20 frames per second of the AI inference. And testing different power profiles of the inference, we show that you can choose lower power dissipation, or you can choose higher peak performance depending on the budgets of your missions, technical budgets that you have. And what is really nice about this, we did all the work on the Leopard DPU eval board model. So the model designed for algorithms prototyping and testing on the ground, compatible with the flight model of the Leopard. As I said, we are treating the testing on the ground very seriously before you will deploy the algorithm in space. So this is also our solution for that challenge, how to test the things on the ground. But going back again to our challenges, all that algorithms that I've just shown you normally cannot work without great data. I mean, data on the proper level of processing. So when you apply the algorithms on the data available on ground, typically use, for instance, level 2 data or so. But to have the same on board is essential to perform all the steps on orbit. So you would require radiometric corrections, atmospherical corrections, georeference, and so on. But the case is even more complex when the pre-processing requires that data that are hardly available on board, like state of the atmosphere to perform the corrections. So once again, here we decided to use deep learning techniques to solve the issue. Our approach was to train our AI models with different atmospherical conditions to automatically compensate for the effects. And actually, we succeeded in that experiment. So we share with you our results in the paper. I really encourage you to read and to to apply in your mission that approach. So in this brief presentation, I think that I shown you that even there are a lot of challenges, we believe that more missions could benefit from the on-orbit processing, will be able to tackle and will be able to tackle those challenges together. So thank you for the attention.